Consider the problem of joining three houses to each of the three separate utilities as shown in figure 1. Is it possible to join these houses and utilities so that none of the connections cross? In this video, we are going to discuss how we can answer such a question. This problem can be modeled using the complete bipartite graph K3 and 3. The original question can be rephrased as: can K3 and 3 be drawn in the plan so that no two of its edges cross? In this video, we will study the question of whether a graph can be drawn in the plan without edges crossing. In particular, we will answer the houses and utilities problem. There are always many ways to represent a graph. When is it possible to find at least one way to represent this graph in a plane without any edges crossing? So first, let us take a definition. A graph is called planar if it can be drawn in the plane without any edges crossing, where a crossing of edges is the intersection of the lines or arcs representing them at a point other than their common endpoint. Such a drawing is called a planar representation of the graph. A graph may be planar even if it's usually drawn with crossings, because it may be possible to draw it in a different way without crossings. So let us take an example so we understand the definition of a planar graph. Is K4 shown in figure 2 with two edges crossing planar? The answer is K4 is a planar because it can be drawn without crossings as shown in figure 3. So the only change we made is we draw one edge in a different way. Maybe by taking a second example, we can understand the concept more. Is Q3 shown in figure 4 planar? Q3 is a planar because it can be drawn without an edges crossing as shown in figure 5. Is K3 and 3 shown in figure 6 planar? Any attempt to draw K3 and 3 in the plane with no edges crossing is doomed. We now show why. In any planar representation of K3 and 3, the vertices V1 and V2 must be connected to both V4 and V5. These four edges form a closed curve that splits the plane into two regions, R1 and R2, as shown in figure 7a. The vertex V3 is in either R1 or R2. When V3 is in R2, the inside of the closed curve, the edges between V3 and V4 and between V3 and V5 separate R2 into two subregions, R21 and R22, as shown in figure 7b. Note that there is no way to place the final vertex V6 without forcing a crossing. If V6 is in R1, then the edge between V6 and V3 cannot be drawn without a crossing. If V6 is in R21, then the edges between V2 and V6 cannot be drawn without a crossing. If V6 is in R22, then the edge between V1 and V6 cannot be drawn without a crossing. A similar argument can be used when V3 is in R1. Example 3 solves the utilities and house problem that we described at the beginning of this video. The three houses and the three utilities cannot be connected in the plane without a crossing. A similar argument can be used to show that K5 is non-planar. Planarity of graphs plays an important role in the design of electronic circuits. We can model a circuit with a graph by representing components of the circuit by vertices and connections between them by edges. We can print a circuit on a single board with no connections crossing if the graph represents the circuit is planar. When this graph is not planar, we must turn to more expensive options. For example, we can partition the vertices in the graph representing the circuit into planar subgraphs. We then construct the circuit using multiple layers. The planarity of a graph is also useful in the design of road networks. Suppose we want to connect a group of cities by roads. We can model a road network connecting these cities using a simple graph with vertices representing the cities and edges representing the highway connecting them. We can build this road network without using underpasses or overpasses if the resulting graph is planar. A planar representation of a graph splits the plane into regions, including an unbounded region. For instance, the planar representation of the graph shown in Figure 9 splits the plane into 6 regions. These are labeled in the figure. Euler showed that all planar representations of a graph split the plane into the same number of regions. He accomplished this by finding a relationship among the number of regions, the number of vertices, and the number of edges of a planar graph. This leads us to the following theorem. Let G be a connected planar simple graph with E edges and V vertices. Let R be the number of regions in a planar representation of G. Then R equal to E minus V plus 2. Euler's formula is illustrated in the following example. Suppose that a connected planar simple graph has 20 vertices, each of degree 3. Into how many regions does a representation of this planar graph split the plane? This graph has 20 vertices, each of degree 3. So V equal 20. Because the sum of the degrees of the vertices, 3V equal 3 multiplied by 20 equals 60, and this is equal to twice the number of edges where we have 2E equals 60. Then E, the number of edges, equal 30. By the formula, we can have the number of regions equals to 12. So let us now discuss the concept of graph coloring in details. Problems related to the coloring of maps of regions, such as maps of parts of the world, have generated many results in graph theory. When a map is colored, two regions with a common border are basically assigned different colors. One way to ensure that two adjacent regions never have the same color is to use a different color for each region. However, this is inefficient, and on maps with many regions, it would be hard to distinguish similar colors. Instead, a small number of colors should be used whenever possible. Consider the problem of determining the least number of colors that can be used to color a map so that adjacent regions never have the same color. For instance, for the map shown on the left in Figure 10, 4 colors are sufficient, but 3 colors are not enough. In the map on the right in Figure 10, 3 colors are sufficient, but 2 are not. Each map in the plane can be represented by a graph. To set up this correspondence, each region of the map is represented by a vertex. Edges connect two vertices if the region represented by these vertices have a common border. Two regions that touch at only one point are not considered adjacent. The resulting graph is called the dual graph of the map. By the way, in which dual graphs of maps are constructed, it is clear that any map in the plane has a planar dual graph. Figure 11 displays the dual graphs that correspond to the maps shown in Figure 10. The problem of coloring the regions of a map is equivalent to the problem of coloring the vertices of the dual graph so that no two adjacent vertices in this graph have the same color. We now define a graph coloring. A coloring of a simple graph is the assignment of a color to each vertex of the graph so that no two adjacent vertices are assigned the same color. Graph can be colored by assigning a different color to each of its vertices. However, for most graphs, a coloring can be found that uses fewer colors than the number of vertices in the graph. So what is the least number of colors that we can use? The chromatic number of a graph is the least number of colors needed for a coloring of this graph. The chromatic number of a graph G is denoted by K x of J. Here x is the Greek letter referred to chi of J. Note that asking for the chromatic number of a planar graph is the same as asking for the minimum number of colors required to color a planar map so that no two adjacent regions are assigned the same color. This question has been studied for more than 100 years. The answer is provided by one of the most famous theorems in mathematics, the four-color theorem. The chromatic number of a planar graph is no greater than 4. Note that the four-color theorem applies only to planar graphs. Non-planar graphs can have a large chromatic numbers, as will be shown in the following example. Two things are required to show that the chromatic number of a graph is k. First, we must show that the graph can be colored with k colors. This can be done by constructing such a coloring, or we must show that the graph cannot be colored using fewer than the k number of colors. What are the chromatic numbers of the graphs G and H shown in figure 11? The chromatic number of G is at least 3 because the vertices A, B, and C must be assigned different colors. To see if G can be colored with 3 colors, assign red to A, blue to B, and green to C. Then D can and must be colored red because it is adjacent to B and C. We already assigned different colors to B and C. Furthermore, E can and must be colored green because it is adjacent only to vertices colored red and blue. And F can and must be colored blue because it is adjacent only to vertices colored red and green. Finally, G can and must be colored red because it is adjacent only to vertices colored blue and green. This produces a coloring of G using exactly 3 colors. Figure 12 displays such a coloring. The graph H is made up of the graph G with an edge connecting A and G. Any attempt to color H using 3 colors must follow the same reasoning as that used to color graph G, except at the last stage when all vertices other than G have been colored. Then, because G is adjacent in H to a vertices colored red, blue, and green, a fourth color, say brown, needs to be used. So H has a chromatic number equal to 4. A coloring of H is shown in figure 12. What is the chromatic number of K of N? A coloring of K of N can be constructed using N colors by assigning a different color to each vertex. Is there a coloring using fewer colors? The answer is no. No two vertices can be assigned the same color because every 2 vertices of this graph are adjacent. So, the chromatic number of K of N is N, that is chi of Kn equal N. Recall that Kn is not planar when N is greater than or equal 5. So this result does not contradict with the 4-color theory. A coloring of K5 using 5 colors is shown in figure 13. What is the chromatic number of the complete bipartite graph K, M, and N where M and N are positive integers? The number of colors needed may seem to depend on M and N. However, as theorem tells us, only 2 colors are needed because K, M, and N is a bipartite graph, so chi of K, M, and N equal to 2. This means that we can color the set of M vertices with 1 color and the set of N vertices with a second color, because edges connect only a vertex from the set of M vertices and a vertex from the set of N vertices. No two adjacent vertices have the same color. A coloring of K, 3 and 4 with two colors is displayed in figure 14. What is the chromatic number of the graph Cn where n greater than or equal 3? Recall that Cn is the cycle with n vertices. We will first consider some individual cases. To begin, let n equal 6. Pick a vertex and color it red. Proceed clockwise in the planar example of C6 shown in figure 15. It is necessary to assign a second color, say blue, to the next vertex reached. Continue in the clockwise direction. The third vertex can be colored red, the fourth vertex blue, and the fifth vertex red. Finally, the sixth vertex, which is adjacent to the first, can be colored blue. So the chromatic number of C6 is 2. Figure 15 displays the coloring constructed here. Next, let n equal 5 and consider C5. Pick a vertex and color it red. Proceeding clockwise, it is necessary to assign the second color, say blue, to the next vertex reached. Continuing in the clockwise direction, the third vertex can be colored red, and the fourth vertex can be colored blue. The fifth vertex cannot be colored either red or blue because it is adjacent to the fourth vertex and the first vertex. Consequently, a third color is required for this vertex. Note that we would have also needed 3 colors if we had colored vertices in the counterclockwise direction. Thus, the chromatic number of C5 is 3. The coloring of C5 using 3 colors is displayed in figure 15. By this video, we have covered many definitions and theorems related to graph theory. As we said before, it is a very important subject for solving serious computing problems. By this, we have finished the graph theory, and we will move into another interesting topic where we will discuss the concepts of trees in computing.